Okay, so let's look at the first one here. What method would you use to solve that first one? Anybody have a preference? Substitution? Perfect. I would subtract 3y from the second one to get 5 minus 3y is equal to x. So now I'm going to take this x here and replace it with this x. I'm going to replace it with 5 minus 3y. So 5 times x becomes 5 times 5 minus 3y minus y equals negative 23. And then we do 5 times 5 is 25. 5 times negative 3y is a negative 15y. Minus y equals negative 23. And then 25 doesn't change, but I combine negative 15y and negative y to get negative 16y. Equals negative 23. And then subtract 25. Negative 16y equals negative 43. And then negative 48, yes, thank you. Divide by negative 16. I was wondering why everybody got quiet all of a sudden. Y equals 3. The little hamster decided not to come to work with me today. So y equals 3. So then we're going to come back up here to this one to find x. X equals 5 times 3 times 3, or minus 3 times 3. 3 times 3 is 9, so 5 minus 9, x equals negative 4. So that is negative 4, comma 3. How many of you got negative 4, 3 for that one? Okay. Number 2 here, what method would that be easiest to solve by? Well, if we see that the equal signs are lined up, the x's are lined up, the y's are lined up, and the constant numbers are lined up. And a bonus, we got negative 5y and positive 5y. That cancels out. So I got 3x plus 7x is 10x. Negative 5 and positive 5y adds up to 0, so that cancels out. Equals negative 19 plus 39 is 20. And then divide by 10, x equals 2. Then what? Put the 2 back into either equation. I'm going to take the bottom one because it's all positives. So it's going to be 7, instead of 7 times x, it's 7 times 2 plus 5y equals 39. 7 times 2 is 14 plus 5y equals 39. We will subtract 14. 5y equals 25, and then divide by 5. Y equals 5. So we've got 2, 5. How many had 2, 5 for the second one? So a few of you even had both of them right. Cool. Guess what that means?
I don't know. You like eggnog?
It's time for a quiz. Now what we're going to talk about here for just a couple minutes before break at least is just a little bit of a venture into material science. And I'm doing this just to show you some applications of where these systems of equations might actually occur someday. Now for you guys, if you just want to be an operator, you won't ever see this. But if you ever want to move up into the next step, into the design and some of the material selection part of the process, this is some of the things you're going to see. So what we have here, this is actually a triple point drawing. It's a 3-phase drawing of a very simple substance. Every substance has a diagram, something similar to this. And what it is, you can see here we have, let me get my pen rolling here. We have solid, liquid, and gas. So the pink over here on the left is solid, the blue in the middle is liquid, and the green on the bottom right is gas. And what we're seeing here, this bottom is temperature. So this is cold here. going up to hotter up here as we move to the right. And then up the left side here is pressure. So for this substance, standard atmospheric pressure, in other words, air pressure if you walked outside on a normal day, would be somewhere in here. At that pressure, you can see it's solid when it's really cold, liquid for middle temperatures, and gas when it's hot. This would be your freezing point or your melting point. This would be your boiling point, your condensing point here, depending on what direction temperature is going. Every substance, and most people don't realize this, but every substance has a point, a pressure, at which if we go below that pressure, there's no longer a liquid phase. How many of you ever dealt with carbon dioxide, otherwise known as dry ice? Yeah. What's the defining characteristic of carbon dioxide? Dry ice. Why do you use it? Why is it called dry ice? It never turns into a liquid. Well, it does turn into a liquid, just not at standard air temperature, atmospheric pressure. Or not temperature, pressure. Standard for carbon dioxide, atmospheric pressure is down here on the diagram. So it goes straight from a solid into a gas. But if we put it in a pressurized hyperbolic chamber, carbon dioxide does have a liquid phase. It's not that it isn't there, it's just it does not exist at standard atmospheric pressure. Does that make sense?
When you put it in the chamber, it raises that line up.
Yeah,
so that it has liquid
it
phase.
pressurizes it so that it goes from this would be 1 atmosphere here, which is your standard atmospheric pressure. The hyperbolic chamber pressurizes it. Almost like a decompression chamber for divers. When it's under enough pressure, there is a liquid form. That's why you can see how this line angles here. It doesn't go straight up, and the same here. That's why when you pressurize water, you can make water freeze at like 50 degrees if you pressurize it enough.
So what if it can be pressurized?
It can be. You can force it to freeze. It can't be compressed, but it can be pressurized and forced to freeze. Here is the diagram for water. You can see this is 1 atmosphere right here. So this is 0 degrees Celsius. That's where it goes from ice to water or water to ice. This is 100 degrees Celsius, where it goes from water to gas to steam back to water. It's what we call the triple point, is that maximum pressure where the liquid phase disappears is 6/1000ths of an atmosphere. So in other words, you take the standard air pressure and reduce it to 0.6% of what the normal air pressure is. So I mean, you really do have to really drastically decrease the pressure. It has to be almost a vacuum.
Yeah, I can't remember the term, but I know there is one. He goes directly from a solid...
Sublimation?
Sublimation.
Yeah, that's your sublimation pressure. Now, you can sublime above that pressure. Snow sublimes. Sublimation means you go straight from a solid to a gas and skip the liquid phase. You've ever had those days where it's below freezing, so the snow's not melting, but the snow pile seems to shrink? And that is pressure related, but not, I mean, you look outside, well, it's got to be standard air pressure. But watch this. If I take this sheet of paper here and I blow on the other side, now if I blow here, obviously my breath pushes the paper up. What happens if I blow over the top of it? Why is it pulling up? Fast moving air is lower pressure than slow moving air. In fact, here, I'm going to pause this for a second, and I'm going to grab this. Since we're talking about it, this would be a great time to play with this. So you saw that ping pong ball of balance in that stream of air. Even if I tipped it, that's because of the low pressure. So you're talking about subliming. That's what's happening in the winter when that snow pile, even though it's below freezing, the snow pile appears to shrink. The wind is blowing past it, and it's creating low enough pressure that it drops down to here. A gust of wind can make a drastic change in air pressure. You ever had it where you have a real strong wind and you turn your back to it so that you're not facing into the wind, and sometimes it's a little bit hard to breathe? That's because that low pressure, you're actually putting yourself in a low pressure pocket, and it's making it tough for you to breathe.
So it's the opposite effect when the submarine goes underwater and you have bubbles of steam right behind it.
Yeah. That's also called cavitation. And that's actually a weird situation. I know I'm getting a little off topic here, but like a boat propeller, if you take a certain boat, if you got a small propeller, if you go from still to full speed as fast as you can, sometimes the boat will just sit there. Well, it's not necessarily making steam. What it is doing is, let's say here's your fin on the propeller and it's turning that way. What it does is it pushes against the water and pushes the water that way, and it pushes the boat that way as it hits the water, right? If a propeller turns too fast, it pushes this water out of the way as it moves, and then the next blade of the propeller comes along and the water has to fill back in behind the prop, the blade of the prop. If it's moving too fast, the water doesn't have time to fill back in. So the water doesn't fill back into the gaps between the prop, the blades, and that blade is just hitting air. So that's why it looks like it's making steam, because it's creating a low, because of its speed, it's creating a low pressure point in the water, and it's causing an air pocket there. It's actually air bubbles that are coming out. And technically, if you could actually get your hand in there without having your fingers chopped off by the prop, it'd actually be fairly cold.
Yeah, it's the same thing for like a submarine that's 2,000 feet under.
Yeah. Yeah. No, it's just air bubbles. Yeah, you crank those props up too fast. That's why you got to accelerate slowly on like a battleship and stuff like that. They have to accelerate slowly. If they, in fact, like an aircraft carrier or something like that, if they try to stop and they try to throw it into reverse to stop, like a speedboat, if you're moving along, you can throw it into reverse to stop quickly. Well, on those big boats, because of their weight and stuff, they throw it in reverse and those props will just cavitate. Also, if you do throw them into reverse too quickly, sometimes you'll actually dump one end of it right down in the water. Pull those props right up into the air. That's an interesting thing to see. Usually it results in whoever is at the controls of the ship at that time being severely disciplined. Anyway, that's off topic. I'm going to get back to this here now. So that's what's called your triple point diagram, and any material has that. Your freezing and thawing points are dependent on temperature. Like I said, it is possible. This is 0 degrees here. It's possible to make water freeze at higher temperatures just by pressurizing it, or to make it go to a gas at lower temperatures, make it evaporate or turn to steam at lower temperatures by changing the pressure. So there's ways you can alter it that way.
So what pressure would you need to get water to freeze at, say, 40 degrees?
I don't know if this diagram would even show it. Okay. And there are limits. I mean, water, like you said, is fairly incompressible. So there's a limit to how far you can take it. This whole supercritical fluid, if you were in a material science class, we'd talk about that. It's kind of like a plasma. We talk about plasmas. They go outside the standard definitions of solid, liquid, and gas. And the temperature can actually change your electrical conductivity and stuff like that. Every substance known to man is conductive electrically, just not at room temperature. You get everything up to about 1,000,000 degrees, everything will conduct electricity. Well, yeah. Really hard to connect it. Yeah. Okay, so here is where I was going to go next. This is a copper-nickel phase diagram. This is an alloy. What we were looking at before was called a unary phase diagram. It's a single substance. This is a binary phase diagram. This is an alloy where we're mixing two substances together. On this end of the chart, down here, we have pure copper. Copper at 1,085 degrees goes from a solid to a liquid. It melts at 1,085 degrees. On this side of the chart, we have pure nickel. Pure nickel goes from solid to liquid or melts at 1,455 degrees Celsius. Now, this diagram does not show pressure. This is assumed to be at 1 atmosphere, at standard atmospheric pressure. This would be 20% nickel and 80% copper, 40% nickel and 60% copper, 60% nickel, 40% copper, and so on. 50-50 right here. So what this is showing, you'll notice pure copper goes from solid to liquid. Pure nickel goes from solid to liquid. If it's an alloy, there's this little band in here. It's what we call the mush stage, where some of it's solid, some of it's liquid. And that's what we're going to talk about when we come back from break. So I'm going to pause right here. Back to this. So anyway, if there's a mixture of two substances, oftentimes there's that slush that occurs instead of going directly from a liquid or a solid to a liquid. I'm going to go down here and find a more, here's a more complex substance. And this substance, again, this is pure, I guess it doesn't say what, this is just a hypothetical substance. This is pure substance A, this is pure substance B. Here it's all liquid, up here here it's all solid, up here it's all liquid. Here it's a mush, and here it's a mush. But here, even though it's a mixture of the two substances, it goes directly from solid to liquid. That's what they would call a eutectic point. You guys are going to work a lot with steel. That's nice. Here, this is a more simple one. This is actually solder. Your liquid, your lead and tin solder. 61.9% tin, 38.1% lead is your best, is your optimal mixture for solder, because that is that mixture, it goes directly from solid to liquid. If you ever done any soldering, you get to the right temperature and all of a sudden just it turns into a puddle. There is no mushy. If you have a solder that's kind of mushy and half melted, it's not real solder. It's the fake, environmentally safe stuff that works like crap. Yeah. Real solder, it does that. It'll be solid, 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 and it gets to the right temperature and all of a sudden just it turns into a puddle. Wonderful to work with. But if it's off on either side of that, it doesn't work so much. This is more complex. This is iron. This is your iron and iron carbon. So this is 0% carbon is pure carbon, or pure iron, pure iron. Right here, that's 0.43% carbon. You hit a eutectic point. You go directly from, it melts. You don't have a mush stage in your steel. Here it is, your 4.3%. Okay, so anyway, back up to this diagram, my simple lead or my copper nickel diagram. Let's say that we have a 60% nickel, 40% copper. So this is 60% nickel right here. I'm going to draw a line there. Come on. Right there. I'll make that a little bit thicker so you can see it. There we go. So there's that line. You guys see that okay? All right. Here, we'll do this again. Ah, crap. There. That'll make it a little easier to see. At 60%, we'll do this, make some horizontal lines here. That's wrong. Grab the wrong thing. Come on. I'm going to have to do this. I'm going to stretch this outside the picture, that way it's easier. There. Now I know I'm getting the line. So here's what I'm going to do. Right there, you can see that's where I'm crossing that 60% line. You see that's just above 1300 degrees. It's about 1308, 1307. This 60% nickel, 40% copper, anything below that temperature, it's solid. right there at almost exactly 1350 degrees, anything above that temperature, it is liquid. But you can see in here, between those two temperatures, it's a mush. Some of it's solid, some of it's liquid. The cool thing is, though, it's not all 60% nickel and 40% copper. In that mush, the liquid has a different composition than the solid. Let's pick a temperature here. So I'm going to take this third line here and I'm going to put it right there, about 1325 degrees. Now I'm going to do a similar thing with that line over here. That's where it's all liquid, where it intersects the edge of that bubble. You can see down here that's not at 60% nickel anymore. It's only about 52% nickel, 53% nickel. This here, if I line it up, right there, you can see that's where that line intersects the edge of the bubble. That comes down here, that's at about 64% nickel and 36% copper. So what we have is this point right here at 1200 or 1325 degrees. It is, let's call that 53%. 53% nickel, which means it's 47% copper. That is the liquid portion. The solid portion right here, you can see down here that's 64% nickel and 36% copper. So you have that 60% nickel, and you want to get a compound that's 64% nickel. You don't have to add more nickel to it, or you want to get an alloy that's 64%. You don't have to add more nickel to it. Raise it up to 1325 degrees and scoop out the solid chunks. The solid chunks will be 64% nickel. What's left over, the liquid, will only be 53% nickel. So if you want to reduce it, you can do the same thing. Now, obviously, if you want to get it below 53% nickel, it's hard to do. So what you'd do is you'd get it down to 53% nickel, then cool it down and do another line somewhere else here and reduce it that way. But yeah, by using the temperature and sifting out solid and liquid, you can alter the content of an alloy. So the question here is, how much of this is liquid and how much of it's solid? Let's say we had 1,000 grams. This is, the WT here means by weight, your composition by weight. Let's say we had 1,000 grams of the 60% nickel, 40% copper. What that means is, what's 60% of 1,000? 600 grams of nickel. 40% of 1,000? 400 grams of copper. Right? Let's say that of that 1,000 grams, X grams becomes liquid. And Y grams become solid. So let's do the first equation to describe the nickel. We know we have 600 grams of nickel. The liquid is 53% nickel. So that's going to be 0.53 times X. 53% of however many grams of the liquid are there is going to be nickel. Plus, we know it's 64% nickel in the solid. So 64 times Y. 0.64 times Y. That's the amount of nickel in the solid substance. That has to add up to 600 grams of nickel. We know there's 400 grams of copper. We know that 0.47 or 47% of the liquid is copper, and 0.36 or 36% of the solid is copper. And now we have a system of equations. So I'm going to go back here where I have more room. 600 equals point, what the heck was that now? 53x plus 0.64y. And 400 equals 0.47x plus 0.36y. So now we can figure out how much of that's liquid and how much of it's solid. Easiest way to solve this is probably by elimination. But I'm going to do elimination a little bit differently than what we've seen. So far, what we've done is we've multiplied both equations by the same number, or by a different number so you get a common denominator. Instead of multiplying, I'm going to divide. Because these are really ugly decimals, finding a common multiple is really ugly. So here's what I'm going to do. Is I'm going to take this whole equation here, and I am going to divide by 0.53. That'll make this a positive 1. I'm going to take this whole equation down here on bottom, and I'm going to divide by not 0.47, but negative 0.47. So that becomes a negative 1. Does that make any sense? Now I'm going to pause it. So they're going to cancel out, yes. So we have 600 divided by 0.53. We get 1132.08 equals, well, that's going to be just 1x, right? Plus 0.64 divided by 0.53. Oops. 1.208 y. Now we got 400 divided by a negative 0.47, negative 851.06 equals, this can be a negative 1x. This will be minus here, 0.36 divided by a negative 0.47 will be a negative 0.766. Now you'll notice that the x's cancel out. In your notes, I want you guys to take a second. See if you can solve that. Okay, so we take the 1132.08 plus the negative 851.06. We get 281.02. The x's cancel out. 1.208y plus negative 0.766y is 0.442y. So we have to divide by 0.442. So 281.02 divided by 0.442. 635.792. This was 635.79 grams. Is y. Y was the solid, right? Right? Yeah, y was solid. So that means 1,000 minus that. 364.21 grams equals x, that's a liquid. What do you think? Not terrible? Probably not something you're going to run out and do on your own anytime soon, but just to show you some examples of this. Other examples of this would be if you were to do a strength analysis of a part. If you had a part that was holding forces like this, let's say it has to hold a gravity load and it's mounted to a bracket here or whatever. You use, okay, you've got vertical forces and horizontal forces and whatever. Maybe it's leaning, it's pinned to a pivot here and it's up against the wall here, so now you've got a force from the wall pushing out. Flagpole, whatever, yeah. the prime example that I can give, the one that just pops into the top of my head, since you mentioned flagpole, would be like a communications pole or electric pole. You've got your wire here. That wire is actually pulling on the pole because it's tensioned wire. Then you got guy wires here that are anchoring it down. Well, that guy wire now has forces going like that. This the electric wire itself is pulling in that direction, and then the pole itself is pushing up to keep everything from being pulled into the ground. Then you can analyze all the forces. Well, you've got X forces and you've got Y forces, and you've got to have the sum of each of them has to equal 0. And you have to solve a system of equations to find the amount of each.
Do they really calculate that, or do they just kind of put it in the ground?
Overdo it. They do calculate, like for this guy wire here, yeah, minimum. This wire here, you can put it out here further and it's going to be just fine, but if you get too close to the pole, it's not going to hold. So they calculate the minimum distance from the pole that has to be. Then if they can't get it that minimum distance, then they know, well, if you put 2 wires that are spread out so far apart, what's the minimum distance from the pole? And 3 wires. So if they can get it further away, they do. If they can't, then they've got to go to 3, 4, 5 wires. And they've got the guidelines say, okay, if you can get no more than 6 feet from the pole, you've got to have at least 4 wires or whatever. Things like that. But somebody had to sit down at one point and calculate that. And if they say, well, hey, you know what? We've got this new type of wire we're going to use. We can increase the tension on the wire to 1,200 pounds of tension instead of 900 pounds of tension. That way it'll sag less between poles. We can put our poles further apart and save money. Well, now there's more tension, so now you got to recalculate where those guide cables are going to go. Okay, well, the good news is Unit 3 is over. I'm going to give you your last 20 minutes here to get started on the unit test. And as promised, you will take it home over break and work on it. I don't know if that's a good promise or a bad one, but you'll get it.